Hi, I'm Alara, and I'm a PhD candidate at Imperial College London. Previously, I was working at Hugging Face as a machine learning engineer on the open source team. Today, I will be doing a code along for the Using Open Source AI Models with Hugging Face project. But let's first talk about what Hugging Face is, since some of you might be unfamiliar. Hugging Face is an AI company with a mission to make finding, using, and experimenting with state of the art AI research much easier for everyone. Almost everything they do is open source, and they have a huge ecosystem of open source tools and libraries. The core component of this ecosystem is their website, also known as the Hub, which functions as a Git platform similar to GitHub. You can use this platform to search for interesting models and datasets by name or by task. And you can do anything that you would on GitHub on the hub, which means that you can git clone repositories, you can create or update existing repositories, you could set them to private, and you could also create organizations. Each model checkpoint and dataset is hosted as a Git repository on the hub. And another really nice feature of the hub is it allows users to store large model and data files in repositories for free. But the ecosystem is more than that. Apart from the hub, Hugging Face has many incredibly popular open source libraries, such as transformers, diffusers, datasets, and much more. You can take a look at the full list of libraries and their documentations on the documentation page. But the ecosystem is even more extensive with their blog, tutorials to use and fine tune models, discussion boards, and also demo spaces where you can play around with hundreds of state of the art models and create your own demos. In this code along, we will focus on the Transformers library and learn how to navigate the Hugging Face hub and how to use transformers and dataset libraries to create custom machine learning pipelines. At the end of the code along, you will have working multilingual text translation and image captioning pipelines, and also your own custom dataset on the hub. Without further ado, let's jump into our workspace and start coding. You will need a Hugging Face account and a token for this code along, because you will be uploading your own dataset. So if you haven't done so, go over to the Getting Started notebook. Make sure that you sign up at Hugging Face and create a token, and come back to the working notebook we have. Let's get started. We will start by setting everything up and importing and installing dependencies that we need. For this project, we are going to use Torch, Transformers, Hugging Face Hub, and dataset libraries. Plus, transformers will need a silent requirement sentence piece since we are going to be using a language model. Both datasets and transformers get updated really quickly with new features. Just to make sure we have the correct versions, run this pip install lines to make sure that we have everything we need. This is going to take a few seconds. And once it's done, you will need to go over to the Run tab and restart the kernel so that we can import the correct versions. I'm going to go ahead and click on that. And done. So the most vital part is, of course, importing transformers. And we can do this by simply typing import transformers. And to make our life just a little bit easier, we will be importing the Hugging Face hub library as hf hub. So just a short alias for us to use. Let's run this code block, and done. We imported everything we needed. In the first task, we will focus on how to load pre-trained models from the hub with transformers. As I already mentioned, the Hugging Face Hub is a Git platform where you can create, clone, and update repositories, as well as store model checkpoints or datasets. Or you can store any type of code you want, really. With that said, Hugging Face libraries such as transformers and diffusers are tightly integrated with the hub, such that they leverage its large file storage functionality to keep the checkpoint and configuration files of each model on the hub as a separate repository. So, how does that work? These two libraries re implement the code of state of the art ML research such that vastly different models can be downloaded and run in a unified way with a few lines of code. And while doing so, they assume that all of the files they need, the configuration files and the model checkpoint, are available on the hub. Notice that each model has its own folder on GitHub transformers, and within those folders, um, each model has its own class that starts with the model name, such as bird for seconds classification. Also notice that some of the models have multiple classes, such as BERT for next sentence prediction, BERT for seconds classification, and BERT for question answering, and so on. So if you're not that familiar with machine learning, and if you would like to get started with an easier way of doing things, um, Hugging Face makes it really easy with the auto classes. Auto classes such as automodel, autotokenizer, autoimage processor, and so on allow users to load a model and its data preprocessor by just inputting the name of a repository on the hub. They are really convenient, as they allow users to load and compare multiple models for the same task without doing multiple imports. It's simple as that. The only thing we will need other than the auto classes is the from pre-trained method, which takes care of figuring out the model or preprocessor architecture and loading it correctly for you. So let's head back to the code. For this task, we will be using a text classification model that is trained on tweets to predict the emoji label. And let's take a look at this model first. If you take a look at the model repo, you will see that there are 20 classes, and each of these classes correspond to an emoji. The model outputs the probability of each class. Let's get the coding and import the autotokenizer and automodel classes from transformers. So as you can see, it's not too much of a mystery. We can just say from transformers import autotokenizer, comma, automodel, and then as I mentioned, we will need the from pre-trained method. Like I said, the from pre-trained method is both convenient and it is also a valid method for almost all main classes. You can use it for auto image processor, auto feature extractor, auto model, and so on. Let's run this code block. A useful thing to know is that while the from pre-trained method looks for a repository with the same name on the hub by default, you can also input a path to a local repository or a URL with the expected folder structure. If you look at the Files tab of any given repository, you will see that it is structured in a certain way. We have a configuration file that includes the labels, the classes, plus architecture specific hyperparameters. It also has the model checkpoints and additional materials such as the vocabulary file for language models. Let's go ahead and print out this tokenizer object we just created. And we can see that this tokenizer is an instance of the Roberta tokenizer fast class. And there are a bunch of other input arguments that might be unfamiliar to you. When you're in doubt, you can simply refer to the Hugging Face transformers documentation to take a look at all of the input arguments and what they do. But perhaps this is a good moment to talk a bit about tokenizers in general. NLP, or natural language models, can't process text inputs as they are, and all of the text input need to be converted to a fixed length mathematical format. All of the tokenizer classes preprocess the text such that each word and punctuation is mapped to a unique ID, also known as a token. Apart from that, short sentences are padded and long sentences are truncated to create fixed sized input vectors. Tokenizers can also use additional tokens to specify the start and end of sentences and to assign token IDs to unknown words that are not included in the original tokenizer vocabulary. The output of the tokenizer tells us that this pre-trained model uses a tokenizer with over 50,000 unique token IDs, and it also applies padding and truncation, and it removes the leading extra white spaces. Let's go ahead and load the pre-trained model as well. Similar to the tokenizer, we will just need to input the name of the repository. And let's take a look at the output. You can see that there are some warnings. Some of them are expected and some of them are not. But if you read closely, you will see that this warning specifically tells us that some of the parameters that were in the checkpoint were not used to load this auto model. And there is a simple reason behind that. This is because all transformer models are designed to have a single base class and multiple task specific prediction classes built on top of it. And the thing is, the auto model class is designed to only handle the base class. It cannot load the parameters of downstream models, such as Roberta for seconds classification. It can only load the Roberta model. In order to identify the exact class name and task of your target checkpoint, you can refer to the model configuration. And that is easy to do. We just retrieve the model config, and then we just print out the model configurations architectures attribute. Let's go ahead and do that. And here we go. This model is an instance of the Roberta for seconds classification class. Let's head back to the transformers documentation and take a look at task-specific automodel classes. As you can see on the right, there are a bunch of automodel classes with names that are closely aligned with model-specific class names we have seen earlier. For example, we saw BERT for sequence classification, and we see that there is a automodel for sequence classification class. Other automodel classes, such as automodel for object detection, automodel for audio classification, and so on, function similarly and are named in a similar manner. So let's head back to our notebook. In this task, we will go ahead and load the same emoji classifier model, but using the correct automodel class this time. We already know that this model is an instance of Roberta for sequence classification. So the correct automodel class for this is automodel for sequence classification. And then similar to the base automodel class, we can just use this class and call the from pretrained methods with the repository name as input to load the model. And see that we haven't gotten any warnings this time because all of the parameters of the checkpoint were loaded correctly. And let's move on to task 3, explicit model and preprocessor class names. This is a really good time to talk about data preprocessors more in depth. We have already seen that language models use tokenizer classes to preprocess data. Similarly, the Transformers library has feature extractor, image processor, and processor classes to preprocess audio, images or videos, and multimodal data respectively. And if you go over to the autoclasses documentation, you will see that similar to model class names, preprocessors can be loaded with autoclasses using their explicit class names. In this task, we will go ahead and use the explicit class names to load the emoji classifier model and its preprocessor. So take a step back. We know the explicit class names of both the model and the tokenizer. We have already seen that the model is an instance of the Roberta for sequence classification class, and the tokenizer is an instance of the Roberta tokenizer fast class. So we just need to import those. From transformers, import Roberta tokenizer fast. And from transformers, import Roberta for sequence classification. Once we have done that, we will be able to use these classes the same way that we use automodel instances and autotokenizer instances. So we just reloaded our tokenizer and model using explicit class names. Note that you can do this for any model. It can be Bird, Roberta, Clip, Bark, all of the models. You learned everything you need to load models correctly, and it's time to put these skills to practice. In the rest of this code along, we will build NLP and multimodal pipelines for text translation and image captioning. And our first mini project is text translation. For this project, we will use the FLAN T5 base model by Google. This is a really powerful model that can perform but is not limited to multilingual translation. You can refer to the model repository to learn all about its capabilities, the tasks it can perform, as well as training details and the full list of languages it supports. Now, Plan T5 is a text to text generation model, which falls under the Transformers Automodel for Seconds to Seconds language modeling class. This class encompasses all language models that perform translation, question answering, and text completion. Same as other language models, the input for this model is the preprocessed output that is converted by the tokenizer. And the tokenizer returns us a bunch of token IDs and attention masks. We have already seen that each token ID represents a unique word, tag, or punctuation in the model's vocabulary. The attention mask in this case just consists of ones and zeros, and it tells the model to attend or ignore certain token IDs. Let's go ahead and start coding. While this task is only about the tokenizer, we are going to need to import the correct model as well. So let's start with that. We are just going to import automodel for seconds to seconds modeling. And then we are going to initialize our tokenizer and model in the same way we learned so far. Done. So the next part is to prepare our input text. And for this example, we are going to be translating an English sentence, "How old are you?" to German. For other language models, this process is way easier. You just input the text you would like to process. But since FLAN T5 is a multilingual model, the first thing we do is giving an instruction specifying which source and target languages to use. So we have translate English to German and then the text we would like to translate. Once we have done that, using the tokenizer or all of the tokenizers in transformers are really straightforward and very intuitive. As you can see, there is only one input it expects from us. And unsurprisingly, it is the input text. Now, we could also make it a named argument, but since it is the main argument, it doesn't really matter. We could also input a list of sentences. Once again, since we have a single sentence, we don't have to do that. The second argument we have is return tensors, and you might be wondering what this PT stands for. It stands for PyTorch, because we would like the output to be PyTorch tensors. Transformers also allow you to return NumPy, JAX, or TensorFlow tensors for ease of use. Once we have done that, we can just preprocess our raw text input, and the output, the preprocessed output, or the input variable we have is a dictionary with the token IDs and attention mask. I'm just going to print out the preprocessed inputs to see everything is going correctly. And done. We have the input IDs, which is the token IDs and the attention mask. Moving on to task 5. We preprocessed the raw text input and converted it to a mathematical format that can be fed into the model. Our next step is performing inference or running a prediction with the model. Let's dive into it. Taking a look at the instructions, notice that our first line of instruction is to use torch.nograd method. This is because PyTorch, which is the deep learning library we are using, performs a lot of computations under the hood. A lot of these computations are not needed during inference, but take up a lot of memory and computing resources. To avoid this, we just specify with torch.nograd and disable it. The actual inference or prediction part is a single line of code. We can just do model.generate and pass in the unpacked dictionary as the input. Remember that inputs is a dictionary with the keys input IDs and attention mask. These stars over here is just unpacking the dictionary and passing in each argument separately. Since we only inputted a single text to translate, the output is a list of length 1. If we had more text to translate, then the length of the list would change accordingly. Let's print out the length of the list to double check this. And yes, it's 1. And let's also print out the outputs. Remember that the input for this model is a list of token IDs. So it only makes sense that the outputs are also token IDs. Since this is not a human readable format, we need to map these token IDs back into the original vocabulary. Luckily for us, transformers make it really easy for us. Tokenizer classes have this really convenient decode method to do this with a single line of code. Let's go ahead and use it. We are just going to call tokenizer dot decode and pass in the outputs as the argument. Let's run this code. And we have the human readable translation over here. Our next task is a short but fun introduction to the datasets library. We have seen that transformers make it easy to load and use pre-trained models. The datasets library do the same thing for datasets. You can search between thousands of datasets on the hub and load datasets with a single line of code. Before diving in, let's take a look at the dataset we are going to use. For this code along, we are going to be using a fashion image captioning dataset with 100 samples, 100 images, and 100 corresponding text captions. Let's head back over to our notebook and start coding. The only thing we are going to need from the datasets library is the load dataset function. So let's go ahead and import it. Once we do that, downloading the dataset is a single line of code. We just call the load dataset function and input the name of the dataset repository. And doing this is going to return a dataset dictionary. Let's take a look. As you can see, we have a dataset dictionary with a trained subset with two features, image and text. So you can think of these features as similar to pandas data frame columns. The number and the name of the features are completely determined by the dataset owner. You will also see that this dataset has 100 data samples, so 100 rows. Let's go ahead and print out the fifth sample within the trained subset. As expected, each data sample is a dictionary of its own. It has the image and text keys where the image is a pillar image. Since this is a pillar image, we can simply retrieve the value of this key and visualize the image within this notebook. Let's go ahead and do that. And we are done. The datasets library has other cool features, such as specifying a specific split. Let's say you only want to download the trained subset or just the validation or test subset. You can easily do this by passing in the split argument and specifying the name of your target split, which is train in our case. Once we do that, it will just download that specific split. And we have everything we need. Once we have done that, we are just going to jump into our next task, which is related to this dataset task. We are going to start building our image captioning pipeline. If you have taken a good look at this fashion image captioning dataset, you have seen that the captions are not that high quality. So maybe you are wondering if we can do better. Luckily for us, Transformers library has quite a few image captioning models we can use. In this task, we are going to be using Blip, an image captioning model by Salesforce. If you are curious about this model, head over to the model repository and take a look at the README. Let's get started. The first thing to mention is that, unlike Flan T5, Blip is not a language model. It is multimodal. So it doesn't fall under the seconds to seconds language modeling class, but under the conditional generation class. In order to use Blip, we will first need to import the Blip processor, since it's multimodal, and Blip for conditional generation. For this task, we are going to be using explicit class names, but you could always switch to using autoprocessor and automodel for conditional generation. So let's quickly initialize our preprocessor and model using the target repository name, Salesforce Blip Image Captioning Base. Once we have done that, it is important to reiterate that all of the preprocessor classes are designed for simplicity, and most of the preprocessors only expect the input data, the raw data, to be preprocessed. So we can simply retrieve the first image sample in our dataset and print out the results. Once again, the results are going to be a dictionary. Since we are inputting an image, the output will be a resized and normalized image. Inference with Blip is almost the same as Flan T5. We will start by setting torch.nograd for memory optimizations, and we will do the prediction with a single line of code. We are going to say output equal to model.generate and pass in our inputs dictionary. Once again, the stars are to unpack the dictionary and pass in the arguments one by one. Once we do that, we are going to have a list of token IDs. Similar to Flan T5, we need to decode this output so that it is human readable. An important thing to mention is that the Blip processor is a multimodal processor. So it encompasses a image processor and a tokenizer. Doing so, it encapsulates all of the methods available to the tokenizer. What I'm saying is that we can simply use the decode method of the tokenizer to output the token IDs in a human readable format with a single line of code. Let's go ahead and do that. Our new caption is a woman wearing a yellow sequin dress. Whether this is a high quality caption or not is arguable, and it is completely dependent on your use case. I think we still did a good job. We came up with a more intuitive but less detailed image caption. For the context of this code along, I will say that this is good enough for us. In this task, you will learn how to create a mapping function to preprocess and generate new captions for all samples in the dataset. In order to do this, we will be creating a utility function named replace caption. This function will be taking a data sample in the form of a dictionary as input. And since our dataset has the image and text keys, the keys expected in this dictionary are image and text. But before jumping into this utility function, let's talk about the mapping functionality of datasets. The datasets library has a incredibly convenient mapping method to apply a function to all of the data samples in the dataset. So you can simply create a function like this. It can be as simple as or as complex as you would want, and then use the map method and input the name of the function to apply it to the whole dataset. Let's head back to our workspace and get started with the code. If you take a look at the code, you will see that almost everything we need is already coded. We have the replace caption utility function, and then on line 18, we are applying the map method. Since we have already seen how to use the map method, we are just going to go ahead and input the name of the function we would like to apply. So I'm just going to say dataset.map replace caption. Now we can take a look at the content of the replace caption function. The content of this function is not any different from what we have done in the previous task. We use the blip processor to preprocess the input image. We feed that to the model to generate a list of token IDs, and then we use the decode method to generate a human readable caption. The only thing we need to do is to overwrite the original caption with this newly generated one. Remember that the original caption is stored under the text feature. So we just say data bracket text bracket equals the caption. Note that I have already run this code block, and since it needs to run this model inference for each data sample, it might take a few minutes. We are now ready to move on to our final task, which is pushing our dataset to the hub. In order to do this, you will need to have an account on the Hugging Face website, and you need to have generated a Hugging Face token. So if you haven't done so, take a look at the Getting Started notebook and make sure that you follow the instructions. Once you have checked you have done all of the setup correctly, you can now log into Hugging Face Hub. In order to do this, I'm just going to retrieve the Hugging Face token from the environment variables. Then I'm going to use the Hugging Face Hub library and call the login method using this token as the input argument. Let's run this code block and see if we can log in successfully. And we were able to log in successfully. The only other thing we will need to do is to push this new dataset to the hub with the push to hub method. Note that this method is not native to datasets, but can also be called for any transformers class instance. So you could also push a preprocessor instance or a model instance to the hub under your own username or to organizations you have access to. I'm going to call this new dataset Fashion Image Caption 100 version 2. So let's upload this dataset and see what it looks like on the website. And you can see that I have a brand new dataset on the hub. Feel free to play around with other models and experiment with everything on the hub.